I'm very glad to have the chance to speak at the Hong Kong Science Museum. And this is a public talk, so we will try to be not as rigorous as we usually do in a lecture, in a university lecture. Instead, I will entertain our audience, online audience, and audience here with a few stories. The story will cover our research, which in my part was only about AI and the computational approach to study quantum materials. So I'm Ziang from Hong Kong U. So actually, much of the story, many of the story was in the web page here. It's from my group. So computation is very hot these days. It's very popular, and people always say that computation is everywhere, right? In particular, right now in this era of big data and AI. And it is somehow the case because as we see every day in our daily life, right? So we have face recognition in this COVID period. And this actually are tracing the people flow, human flow. These are big data, nothing but big data. And we also heard about the story a few years back of the AlphaGo. I think many of us know that the machine actually beat human beings in terms of playing Go. And this particular snapshot is actually from this news, was this Chinese Go player, Jie Ke in Chinese. He was number one, I think, at the year of 2017. And he played with AlphaGo and he lost the game. And this is actually how he actually cried during the game because it's just too hard for him. And there were some quotations of what he said, right? The machine plays perfect, that AlphaGo is not the goal, is not God, but is a superior species than human beings. So what he is saying is that the computation capability of the machine is so powerful that it's beyond the human capability. And actually now we know the so-called AlphaGo is not so complicated. It's just a simple 12-layer convolutional neural network. So we know how it worked, and it actually behaves better than human being. And of course, we also see there's so many usage of this AI and computation. For example, these robots, right? I think here I put a link to this famous company, Boston Dynamics, that we can see a video that how this robot dog, I think it's called a Spot, how it works. I think this is quite entertaining. So let's have a look of this, just for a few seconds. So this is how the machine robot dogs work. Of course, this is related with mechanical engineering, electrical engineering, but there's also computation behind. There's how the equipment can react with different environment, how it turn around, how it's detecting the obstacles in front of it. So this is quite amazing, and it is partially because of the computation that make this possible. I think we can go. You can open the door as well. It also works in different climates, like carry stuff. How human beings interact with the machine. You type code, the machine will react with the code. With the programming, basically, we can study another one. So I think this just, okay, I can stop here. Let me go back to my slides. Right, so what I want to say is that robots and also the self-driving car, this is a real picture. I think it's taken from this West Kowloon culture district that the car is just driving by itself. So behind all this is a computation. It is so, because of this, it is true that the data and the AI is coming to our life every day. But another thing I want to remind everybody is that actually computation is also a very old subject. It has a very rich history, and it actually has a very interesting history, in particular related with Hong Kong, I want to talk about. That, I think probably very few people actually knows there's an interesting relation between the modern Monte Carlo simulation technique and the Opium War and Hong Kong. So Monte Carlo is a simulation techniques people use for many in science, in engineering. It's very commonly used. But this method, this numerical method, actually related with us in a very interesting way. So Monte Carlo, as people know, is a place. It's named after a place. The place is this city-state, Monaco, in southern France, in a very beautiful Mediterranean Sea. And in this city-state, there's an area called Monte Carlo. There's a district called Monte Carlo. That in the year of 1865, people opens a casino. The casino is called the Casino di Monte Carlo. So it is from here that this randomness, this sampling, this method of using randomness to compute things starts from. So it starts from gambling. And actually, this is part of the reason this casino become popular is related with us in a way that if you learn a little bit about history, this was roughly the time of the Qing, especially late Qing dynasty. So this was the year where the so-called second Opium War took place. And in the second Opium War, it was French and also Britain. They came and they fight with the Qing dynasty. And of course, the Qing dynasty was so backward, they lose the war. And part of the consequence was that for those people we know, this is a famous place in Beijing. It's called the Old Summer Palace, or in Chinese called Yuanmingyuan. So it was burned down because of the war. And it's also related with Hong Kong was that there was a treaty back then signed. It's called the Convention of Peking, that Kowloon was given to Britain. So actually where we stand right now, I think was somewhere here, was given under British rule after the Second Opium War. And not only these places, or this palace, but also the Qing dynasty at that time have to give Britain and French this 8 million tallies of silver. So it's real, like a treaty, like a penalty they have to pay. And if you think about this time actually was that about the time that the people took this money and they eventually went back to Monte Carlo to play, to gamble, and partially make this place so popular. So this is, a very interesting link that the Chinese people in the late Qing dynasty was very backward. We are very far behind from the European civilizations, but we still contribute in our own way into establishing this international scale of performing computation and develop numerical method. So this is a kind of a funny twist, funny link in history. So this is old. So computation is actually old. But computation is also new. So in our daily research of quantum materials, we use computation to study we call quantum bit or quantum entanglement. I think many of you maybe heard about that. For example, this story about Schrödinger's cat, that a cat can be live or dead, depends on whether you measure it. So this is actually the situation where one electron sitting in an atom, for example, electron in a hydrogen atom. So the hydrogen atom has a proton and has one electron. And we can characterize the property of these electrons with 0 or 1, a bit. And depends whether we measure it, it's either 0, sometimes 0, sometimes it's 1. So that means one electron has 2 degrees of freedom. But how about 2 electrons? If we go to helium atom, there are 2 electrons. Each of the electrons has 2 degrees of freedom. So 2 electrons has 4 degrees of freedom. So we can add this. We can go through the periodic table, but very quickly we will see we run into problem. Because the degree of freedom increased very fast. It increased in this so-called exponential manner. So 2 multiply with 2, multiply with 2. So you can check how large this number grows. For example, as I said, when there's 1 electron, only 2 degrees of freedom. When there are 2 electrons, there are 4 degrees of freedom. But when there are just 10 electrons, 2 to the power of 10 is already 1,000. It's 1,000 degrees of freedom that we have to compute. And just going down the ladder, 20 is 1,000,000, 30 is 1,000 million, it's 1 billion, and so on and so forth. So actually, human beings, even these days, when we use our best computers, supercomputers, we can exactly treat only 40 or 50 electrons. So this is where we are actually these days, if we want to solve the exponential problem brute forcely. But actually, 40 or 50 electrons was even less than the number of electrons in many of the simple elements in the periodic table, say iron, a silver, a gold. They have more than 40 or 50 electrons. So how do we do with that? So this is the difficulty we are facing. Our world, our quantum world, is exponentially complicated. So we have to face this problem. And this is actually a problem, as I just said, computation is also old. It's actually a problem also our ancestors already realized. So there's also a story about this game of chess, if you know, that there was this ancient Indian person, Caesar, who was famous for invent the game of chess. And the king want to give him some prize for this invention, and the king was asking him what can he offer. And Caesar, as a smart person, he said, how about let's just put a green on my chessboard, and for each set of the chessboard, let's double the number of green. So the king was simple-minded. He said, of course, this is a simple game. It's only 64 set. You can just put many greens there. But if you really compute, so one side has 1 green, and another side has 2, and 4, and 8, and 16, and so on and so forth. If you go to the end, that is a number already 2 to the power of 64 minus 1. So this is an exponentially large number. So if you take this number literally, this number actually translates into this number, this many of tons, and it's actually 1,000 times more than the global production of wheat, even these days. So Caesar, as our ancestors, already realized this problem. So the world is exponentially complicated. I mean, our quantum world is also exponentially complicated. So we have to solve them. If we want to solve them brute forcely, we will hit the so-called exponential wall. So the way to go is to, on the one hand, develop better computation equipment, on the other hand, to find a better method, such as the Monte Carlo method, that actually can solve this exponential problem in a polynomial time. So this is important in the algorithm part. But computation really coming to us these days, right? It's coming to us. It's also because even we hit the problem exponentially, it's still relatively easy. It's still relatively easy because the semiconductor industry and the computational facilities are growing so fast. So as we see here, so this is a chart describing the so-called Moore's law. So Moore's law is an empirical law in the semiconductor business that the number of transistors on the microchip doubles every 2 years. So basically that means the speed of computation doubles every 2 years. So in this semi-log plot, it's a straight line. So the dots stands for different type of CPUs, if you like. So the law have been working for 50 years and is still working. So the facility of computation is increased exponentially as well. And the one typical way to characterize this type of computation facility is this thing called the floating point operation per second, flops. Maybe some of you heard about this. So when we judge how good the CPU is, we're talking about what number of flops. So there are some certain language, for example, 10 to the power of 9 flops is called a gigaflop. 10 to the power of 12 is called a teraflop, petaflop, exaflop, and so on and so forth. So our personal computer these days, our laptop, for example, is already in a number of 10 to the power of 10 or 10 to the power of 11. So it's between the gigaflop and the teraflop. our computer is already very fast. But still, when we compare this with a human brain, actually it's still less than a human brain. Human brain has been estimated that 1 second can perform 10 to the power of 17 operations. So our computer is still slower than human brain, our laptop, I want to say. But if we put a lot of laptops together, we make these supercomputers these days, we may actually win because as you can see, that close to us, so for example, this is one of the supercomputers in China. This is called the Tianhe-1 in the National Supercomputer Center in Tianjin. That this machine actually has a 5 petaflop computation capability. 5 petaflop means 10 to the power of 15. So it's still less than human brain. But this is another computer. It's called the K computer in Japan. That is already twice larger, faster than the Tianhe-1. And this is the Tianhe-2 in the National Supercomputer Center in Guangzhou. It's close to us. It's already 100 petaflop. So this is already at the scale of the human brain. So this is actually part of my research was carried out in this machine. And these days, people are talking about this extraflop, this new generation of computers, both in China, in Japan, or this is also in China, and also in the US, in Europe. People are developing faster and faster machines that actually helped us to solve the problem. So what I want to say is that computation comes quick. Computation is coming to us every day. Computation is old, but computation is also new. The facilities is developing very fast. We have also very good algorithms, so we can use this combined together to solve a lot of difficult problems. And from here on, I will share with with you some of our research stories that we use the computation to solve, use AI and computation to solve realistic quantum problems. And of course, here, I really have to sacrifice the scientific rigor. I have to talk about the stories in a more common language. But let's see. So for example, the first piece of story I want to share with you was that recently we have performed computation through my team in Hong Kong and my collaborators in Beijing and Shanghai. So we actually use computation to connect people over China. That we study a particular quantum material. This is a particular quantum material made of these 4 elements, thallium, magnetism, gallium, and oxide, TMGO, for example. And in this material, that this thallium atom, or ions, if you like, form this special kind of triangle lattice. And the electrons on the lattice interact in a very strange way, or very interesting way. So the problem is that the chemists, they design or they grow this material, they perform some measurement, but they didn't know what is the microscopic model of this material. So it is our task to check the model. So our friends, our collaborators in mainland China grow the material, perform some measurement. The so-called measurements means some thermodynamic data. That means I measure how the material responds as a function of temperature. I get different kind of curves. And from some simple physical understanding, we can write a simple model of the materials, and we compute the property, the corresponding property of the model with this exponential data. And we can check whether our model is good or not. Of course, in the initial guess, always not good. So we have to scan the so-called parameter space to fit our data with the numerical data with the experiment result. But this is where AI enters. So we can use machine learning to make a good prediction to help us to go from one set of parameters to the next set in a fast speed. So this is technology term is called Bayesian optimization. We use this optimization method to adjust our model and redo the computation and compare with the experiment. And instead of scanning all over the place of the parameter space, we can go from somewhere remote, and very quickly we can move to the center. So this is where AI helps us to speed up the simulations. And with this technique, we can get the accurate numbers of these parameters for this macroscopic system. And we can compute the response of the system and compare with the experiment. I think here in this chart, the dots is what we computed, and the green lines is actually what the experimenters see. So they match perfectly. So in this way, we can demystify the real material. So not only this, we get the models, we can learn something more beyond what the experimentalist has seen. We found the model, we look at the model, we found actually that model has very interesting topological properties that has been overlooked by the experimentalist in the first place. So we get the parameter data, we compute this parameter data, we predict that in some area of the model, in some temperature region, they should see some new phenomenon that they have not seen in the first place. So then we contact our experimental colleagues in mainland that, to perform this so-called nuclear magnetic resonance measurement. So this is actually the medical correspondence of CT if you do in the hospital. So you do the CT, we do the CT on this mineral instead of on human beings. So we tell them between certain temperatures, they should see this response, and they do the experiment, they do find this response. So this is actually how the modern collaboration works, that we get some raw data from the experimentalist, we dig out the data and find the model properly, and we make new predictions and tell the experimentalist to do the new measurement. And in this way, we can fully understand the material. And this material, actually, this property, this topological property, is actually related with this Nobel Prize Physics of 2016. So this phase, this new phase between these two temperatures is called the KT phase. Was named after Castells and Solis, but two of the Nobel laureate of 2016 Nobel Prize. So this is related with a new way of seeing the material in a topological fashion. But at this point, you might ask me that what I told you is too abstract. This has nothing to do with everyday life, right? This is good, but it's not connected to people. But how do we connect to people? I think I have some new stories, other stories. So for example, every day we use electricity, right? I think the computation and AI could be the solution for the energy crisis, to help us to solve the energy crisis. This is related with electricity. For example, our electricity is generated in Hong Kong, was generated from CLP, that they use the high voltage to transmission electricity from the power stations. But on the way, the electricity going through the wire to our house, a lot of the energy has been wasted, because when the electrons are traveling in the wires, they feel the resistivity. Resistivity generates heat. The heat will just evaporate into the air. So a lot of the electricity actually has been lost on the way going from power station to our house. Can we solve this? Can we find better materials that do not generate heat, do not lose electricity? This is one thing we can answer. Another thing is actually in Hong Kong, we now have this high-speed rail, right? We connected in the normal time, not in the COVID time, but in normal time, we can go to Beijing in 10 hours, if you like. So 10 hours is still too long. In fact, actually, once I took my daughter with me, take this train from Shenzhen to Beijing, you probably do not want to lose a whole day on this train. It's just too long. Are there solutions? Can we build a faster train with better materials? There are solutions, actually. People are testing. There are these magnetic levitation bullet trains. These trains can go 600 kilometers per hour. The trick is that you have to levitate the whole train in the air and let it flow. But how do you levitate a train? You need strong magnetic field. How do you have strong magnetic field? You need a strong current. How do you generate a strong current? You have to the strong power stations. But when the strong power station send you the strong current, it will generate so much heat because of the resistivity that the wire will already melt. So this needs some new materials. Can we have some better materials that help us to go build a faster train, help us to solve the loss of electricity on the transmission? There are solutions, actually. There are solutions. And these solutions is related with a thing called superconductivity. So we actually have material that do not have resistivity. This is called superconductivity or superconductors. And these materials has already been discovered more than 100 years ago. This was first discovered by Onnes, a Dutch physicist, in 1911. That he observed mercury, the kind of metal, that mercury loses its resistivity at the temperature 4.2 Kelvin. So this is the resistivity, this is temperature. So below 4.2 Kelvin, this metal has no resistivity. So this is the ideal material we're looking for. The only problem is that the temperature is too low. So 4 Kelvin translated to Celsius is almost minus 300 Celsius. So on our planet Earth, there's no place. Actually, the absolute temperature is only minus 273. So this is just too low in any realistic applications. But can we find new materials that actually go from, let's say, minus 300 Celsius, let's say, to minus 100 Celsius, or to room temperature? Can we find a material that shows superconductivity, but works at this room temperatures? So there are materials. So this superconductor, which shows superconductivity at a very low temperature, is called conventional superconductors. So there are a new class of material which shows superconductivity not at minus 300, but at minus 100. This is called high temperature superconductors. So these are the materials that has been discovered around the 1980s. So we have material which might be applicable in somewhere in Siberia or in the North and South Pole already for daily usage. But the problem is that we still want this material to work at even higher temperature. So the problem is that we do not know why this material worked in the first place. Because these are all these compounds, these chemical elements. So what it boils down to is these copper ions formed in this two-dimensional lattice. Each carries some of the electrons, and electrons are moving on this lattice, and the electrons are interacting with each other. The problem boils down to how do we deal with hundreds, thousands, millions of these quantum mechanical electrons interact in a quantum mechanical way. We cannot solve them even now. So that was the issue. If we do not understand why this material is working at minus 100 Kelvin, how can we make a new material that works at room temperature, for example? So we should understand this in the first place. And this actually is where computations comes. So people are still working on this, and actually part of my research is related with solving this problem. So for example, we developed this so-called self-learning Monte Carlo method. This is a new method that uses AI technique to solve the problem. So what I mean is the following, that in a technical term, we have to build a model for these high temperature superconductor materials. The model usually are this lattice model we call, and we put the electrons on this lattice. And we have to solve this model by computation. And I shouldn't explain this. I should not explain this. This is mathematical formula. But what I want to say is that our conventional method is a method to trace how these electrons are moved in this material in any space and time. And we have to trace this material by this determinate computation. And this computation is very costly. It is not exponential, but it's polynomial with a very high power. So the best method so far actually scales with the number of electrons to the power of 3. So it's polynomial, it's not exponential, it's polynomial, but with a very high power. So these days, even you use those 10-He machines I just mentioned, you can only solve the problem with roughly 1,000 electrons. That we can understand partially. But the real material, this material, what I was talking about, there are millions, billions of electrons interacting on the lattice, and this is way larger than this small 1,000. So we need a better method. And one of the methods we try to come up with is this self-learning Monte Carlo. It works in the following way. That is, when I simulate my electrons living in this strange lattice, when the electrons are moving, I try to record the movement of the system. And actually, I know these electrons, they are somehow like human beings. You know, when they interact with each other, they form new structure. They form new structure, and this new structure talk to each other. So we need to capture this new structure that one unit is not a human being, but maybe 10, but maybe a million. And in this way, that we can reduce the number of degree of freedom and describe the system under this new structure. So this is where our self-learning comes about, that we look at the environment, we look at the evolution of these electrons in the conventional simulations. But we think, so this is meant to be a brain. We think that how can we write the effective models which capture the interaction, the effective interaction of these new structures of these electrons. So these new structures are simpler than the original ones, and they capture the essence of the system. So if we can look at the original simulations and use our machine learning technique to extract these effective interactions, we can simulate the system in a larger size. So effectively, that means that we usually, when we want to get the solutions, we want to climb up a lot of these so-called energy barriers. Usually, you do not want to go small step because you don't change much. But you also do not want to go to very large step, very bold large step that actually costs a lot of energy. What you are looking for is this low energy space of the system that is where this new unit are talking to each other. So we use our machine learning to extract this interaction between this new unit. Effectively, we can solve the system in a larger size. So what we have achieved so far was that instead of to the n of 3, we can reduce to n of 2, for example. So it's still very high, but it's already better. And on this way, we can use different methods. So this is a method we name it, we call it emus. Emus is an Australian version of ostrich. This bird helps us to solve the simulation. This is actually one structure of how it stands for how we structure the data. And of course, we can use the neural network to solve this problem. So in this way, that we develop new methods that effectively help us to solve this system. And the hope is that with this method, we can capture the true physics ingredient of this, for example, high temperature superconductivity. We can understand why this material become high temperature superconductor at minus 100 Kelvin. So for example, we can design models now. We can design these models of electrons interacting in this complicated way, but it shows this so-called quantum critical phenomenon that is supposedly to happen under this so-called superconductivity doom. And we can design models that study the evolution of the electrons from one type of metal to another type of metal, which is corresponding to different part of the phase diagram of this material, that in somewhere this so-called Fermi surface is large, in somewhere the Fermi surface is small. So our model really actually captured this phenomenon. And our model even captured this very interesting phenomenon that some of the so-called Fermi surface grow from this full surface to the small pocket of the arc, and our simulations really reproduce this full Fermi surface and the small arc. So in this way, our model actually reproduce the method, and this gives us confidence that our model correctly describes the low energy degree of freedom of the system. With this understanding, we can design better models. And of course, the simulation also can give some other new understanding, which not only in our material science, also related with high energy physics. But that's, let me skip this. So this is what I want to say is that with the computation, we can not only answer our abstract, purely scientific curiosity, but we also try to help to understand this material that could solve the energy crisis, that could help us to build faster train. And these kind of examples are in a lot of places. So for example, computation and AI can also help us to design better face masks. I just learned recently. So this is a part about the graphene. So it's another new type of quantum material that this graphene is coming from the graphite. So graphite basically is our pencil. In our pencil, the carbon atoms form these layered structures. And each of the layers are connected by the so-called van der Waals force. So graphite is the bulk material, and it turns out that each of these layers can be peeled off by human beings. We can peel each of the layer off to generate this pure two-dimensional material. This is called graphene. And this is actually discovered in the year of it's discovered in the year, I think it was 2004 or 2005, by these two gentlemen, Guy and Nostalov, that they was given also the Nobel Physics Prize in 2010. And their way of finding this material is really as what I said. They just use a Scotch tape, put on the graphite, and peel it off, And that actually generates these layers of the material. These layers is the graphene. So the graphene itself would generate a lot of activity, I think around around this time. And this was actually the prediction. At that time, people say the graphene can be used into many different places. For example, in this is electric payment, right? In this mobile phones and in the solar cell and so on and so forth. And actually, many of this we are using after 10 years. We are using this already, right? So many of these predictions at that time already came true. So graphene was one of the ideal material that can do a lot of magic things. And I was just found recently, actually, this was one thing I saw on the subway, that people now start to use graphene to make new face masks. And supposedly this will help us to fight the COVID. And this is actually, I think it's a Hong Kong company that produced this type of masks. And at some point, maybe we can think about buying this for yourself. So this is the graphene. And another thing I want to say is that Guy, this person who actually got this Nobel Prize, he's a very interesting physicist, very interesting scientist. He not only got the Nobel Prize, physics prize, he also got this so-called Ig Nobel Prize. So there was this funny Nobel Prize that given to a scientist who is doing some funny experiment or funny discoveries. And his prize, it was even before his Nobel Prize, was that he put a frog in a strong magnetic field, and the frog has been leviated. So the frog, because of the so-called diamagnetism phenomenon, can fly in the air. And this is an early version of this train, what I'm talking about. So scientists, sometimes we do kind of, at that time, maybe just pure kind of fun, but it might come true at some point. So this is graphene guy. But the thing is that this is already 10 years old. Recent years, I think maybe 2 or 3 years by now, that the graphene has a new twist. Graphene becomes even more important as a quantum material because people really twist the graphene. So if you put a 2 layer of a graphene and just twist it by a so-called magic angle, which is around 1 degree, people discovered that this twisted bilayer graphene has superconductivity. So graphene was just a very good semiconductor, but now if we put 2 layers of them together and twist it, we found it's become a superconductor. So this was the schematic plot, and this is some realistic data just to show that the resistivity of this twisted bilayer graphene at some parameter range become very small. It's almost 0. So for example, in some range of the condition, of the experimental condition, the system becomes a superconductor. So this is a new material, like this high temperature superconductor I was talking about, that also shows this property of superconductivity, that we can make use of them into electric wires to transmit electricity, transmit energy. We can use them maybe to build this levitated train. So these are new materials which has just been discovered. This new phenomenon has just been discovered in 3 years back. I think it was 2 or 3 years back. So this is very recent, and people now, physicists all over the world, start to study this phenomenon. The motivation of this is that we want to understand why this material becomes a superconductor. Similar as we want to understand why high temperature superconductor become high temperature superconductor. If we can find these reasons, we can design better materials. And this material, similar as the high temperature superconductor material, also goes to interacting electrons on the system. Millions, billions of electrons interacting with each other. And we have to solve them with better method. We cannot solve them with brute forcefully with only the big supercomputers. We need to design better method. And this is also where we came to help, that we design this, I don't have time to explain, but we designed this so-called momentum space quantum Monte Carlo method. That is a method that captures the model of the system And we compute the property of the system and compare with experiment, get some first-hand understanding. And actually our method, this was actually one of the, this is the Chinese physics letter journal, that our method was come to the cover story of this journal, that this is where the development of algorithms combined with the development of computation helped us to understand the development of quantum material. So on top of this, so of course we still know very less of this system. We cannot explain the whole, let's say, phase diagram. We can only understand it partially at the moment. For example, we can understand why this material also become not only superconductor but also topological. So we have some models, we have some understanding of this. So all of this, I just want to say that computation comes with this method development. Come with this platform development helps us to do cutting-edge research in quantum material research. And I think with this, I can already stop with my part of the presentation, just to, by this storytelling, that I give you a flavor of how do we do the research using AI and using computation to help not only satisfy our scientific curiosity, but also help the society to move forward.
Hello everyone. Thank you very much, the Hong Kong Science Museum, for giving me the opportunity to give this talk. Thank you very much who is online. I hope you would all be in the room, but this is how it is. So we're going to completely change scale from the previous talk, and going from the quantum mechanics, the quantum world that Dr. Ziyang talked about, we're going to move to a much larger scale, and we're going to go to the astrophysics world. So maybe if we want to understand why we need such big computers to do astrophysics, we should start by understanding how big is the universe, and maybe look at a brief map of our universe, at least the way we know it today. So how big is the universe? And let's start with, very simple, the solar system. So on the left, you have the sun, and then you have the 8 planets. We live on Earth, the 3rd planet, and this image is to scale. That is, you can see how small is the Earth compared with Jupiter and Saturn, for instance, but also how small are all the planets compared with the sun. And one interesting question that we can ask ourselves from this image is, what is the width of this image? How far is Neptune from the center of the sun? And if we use the units that we're used to use, that are kilometers, it's about 4 billion kilometers. And you see that this is already a very large number. And because we're going to go to much larger scales, actually, we will stop using kilometers, and we will instead use light hours or light years. So light is made of photons that are grains of light, and they travel at 300,000 kilometers per second. That is the fastest speed that is reachable with the physics that we know. And when we talk about light hours, it means that for photons that travel at 300,000 kilometers per second, it's going to take 4 hours. So it takes 4 hours to go from the center of the sun to Neptune. To give you an idea, it takes only 8 minutes to go from the center of the sun to Earth. So this shows you how big in the universe. And actually, we're going to have to use even larger units, larger than light hours, and we're going to use light years. So a light year is the distance that is crossed by a photon, so again traveling at 300,000 kilometers per second, during an entire year. So for now, this number seems pretty small, 0.0005 light years, but you will see that when we go to larger scales, we'll reach reasonable numbers. So how does the solar system look in the solar neighborhood? you see that the sun is in the center and you have all the neighboring stars in the area. Again, we can play the same game and we can look at the width of this image. It's about 1 million of billions kilometers. So as I told you, kilometers will not be useful anymore because the numbers are going to go so high that it's going to be way more useful to use light hours or light years. So the scale is about 150 light years. So it means that it takes roughly 150 years to go from a photon that is emitted by the sun in the center of the image to the outer part of the image. Just for information, the closest star to us, Alpha Centauri, is about 3 to 4 light years from us. That is, when you look at Alpha Centauri, the photon that you see from the star was actually emitted 3 to 4 years ago. Let's keep moving in your universe, keep zooming out, and look at our galaxy. So you've all seen these images of galaxies. So this is obviously not our Milky Way because we cannot look at it since we're inside, but we believe our Milky Way kind of looks like that. It's a beautiful spiral galaxy, and the sun is located in the outskirts of the galaxies. Again, what is the width of this image? Well, it's too many kilometers. We will not use this unit anymore. It's too many light hours, and we will stick to using light years. The radius of the Milky Way is about half of the width of this image, and it's 25,000 light years. So I insist again, it means that when we look at the center of our Milky Way, we actually look 25,000 years ago because the light that has been emitted from there took 25,000 years to go from the center of the Milky Way to our eyes. But actually, there are many galaxies, and we can keep zooming out. And we now look at the local group. In the lower right corner of this image, you see Andromeda Galaxy that you can see if you look at the sky, very clear sky, when you are in the southern hemisphere of Earth, so not from Hong Kong. And again, we can keep doing the same exercise, looking at the distance. And the distance to Andromeda Galaxy is about 5 million light years. So again, I insist, it's going to take 5 million light years to go from Andromeda to us. But this is not, again, the end of the story. This is only the local group. We can keep zooming out, and then we see what we call the large structures. You see every dot here on this image is a galaxy that is the size of our Milky Way, and the width of this image is about 400 million light years, okay? And actually, we could keep zooming out, but then the picture would look very similar. It's self-similar when we go to larger scale. This means that when you keep zooming out, you will keep having this image, this filamentary image that we call the cosmic web. So the universe is big. It takes a photon 4 hours to go from the center of the sun to the farthest planet, to cross the solar system. It takes a photon 30,000 years to go from the center of the Milky Way to our Earth, and it takes millions of billions of years to go to other galaxies. And astrophysics is the study of all this. That is a very wide range of topics, a very wide range of scales, and this is why we actually need computers, because we're going to have to simulate all this in a comprehensive way such that everything is somewhat consistent. So how do we do that? Well, we're going to use computers, and we're going to do computational research in a similar way as presented in the first talk. So let's start very simple, just to explain you in a slightly different manner than has been explained in the first talk, what I mean by computational research. Assume on the top left corner of this image that you have a tennis ball. And then you throw this tennis ball to the air with a speed v0, which is about 10 meters per second. And I'm a tall person, I'm about 2 meters. So the initial height of the tennis ball is about 2 meters. What's going to happen is that the ball is going to go up, it's going to slow down. At some point, it will reach the maximum height, and then it will go down to my hand. Another way that we can look at it is on a graph. So here, what I'm showing is the height of the ball on the y-axis, which I call y, and they are expressed in meters. And on the x-axis, you have the time in seconds. So you see initially, at the beginning, when I throw the ball at t is equal to 0 seconds, the ball is about at 2 meters. Then it goes up, it goes up, it goes up. After about 1 second, it reaches a maximum, and then it goes down, and I don't catch it. So it hits the floor in about 2 to 2.5 seconds. So what you need, actually, you see, you just need the initial velocity, the initial height, and a set of equations. To understand this problem, you need what we call Newton equations, Newton's law. This is the simplest thing that you could learn in first-year university physics. And if you have a set of equations and initial conditions, you have everything to understand the problem. What you just need to do is actually to solve these equations. And if you have done some physics at the university, if you have done some basic calculus, you can actually solve this equation and find the solution. Okay? So the height depends on the initial height, 2 meters, the initial velocity times the time, and then you have some factor with the t-square, which comes from the fact that the ball is pulled by gravity. And if you give me a time, say 1 second, I can replace the t here in this equation, and I can know at which height is the ball. And this means that we have an analytical solution to this problem. This means that we have solved analytically the problem. But in some cases, and actually in most cases today, we cannot find an analytical solution. It's not that it doesn't exist. It's just that we do not have the math capabilities to find this solution. And it has been shown a lot of examples in the previous talk, but basically most of the research today face this problem. So how do we do? Well, we use a numerical approach, and this is why we're going to use very big computers. I'm explaining here the idea. So if I walk at 5 meters per second, okay, you can say that in 1 second, I'm going to be 5 meters from my position. And this is exactly the idea that we're going to use. We know that initially the ball is at 2 meters per second, and we know that its velocity is 10 meters per second. So we can know that in 1 second, it's going to be in around 10 meters from its position. And we're going to do step by step, we're going to evolve this equation. And this is what we have if we take a time step of 0.5 seconds. So you see, initially the ball is here, and then we estimate the position 0.5 seconds after, again 0.5 seconds after, again 0.5 seconds after, and this is the dynamics that we find for this ball. So you can see that there is a lot of discreteness. We have the position every 0.5 seconds. So what we may want to do is to actually reduce what we call the time step, which I named delta t here, and maybe go to 0.1 second. So now, instead of having a point every 0.5 seconds, we have a point every 0.1 second. And you see that it's much smoother, it's much better. But it's still a bit incorrect. We still have a lot of errors. But it's not so bad, because we didn't have to do all the calculation. We can just give this to a computer, and the computer is simply doing some addition and multiplication. Very simple operations, but a lot of them. And we don't want to do them with our hands, but we can ask the computer to do them. If we want to have an even better approximation, we can reduce again the time step, 0.01 second. And you see now that the numerical solution is very close to the analytical solution. And you can show, and this is very important in science, that you have converged. Because if you take an even smaller time step, 10 times lower, 1/1000th of a second, you find the exact same solution. This means that if you keep going down in time step, you will still find the same result. But obviously, you always have to go to around 2 seconds. So for this one, you need 200 time step. For this one, you need 2000 time step. So when you take a smaller time step, then you need to go to a bigger computer because it's very time consuming. And this is exactly the idea that we're going to use to solve our astrophysical problems. We still have a set of equations. Simply, the equations are a bit more complex. We have some hydrodynamics, which governs how fluids evolve, how gas evolves. We have some mechanics, which we have seen earlier, which tells you how planets move around the sun, how stars move when they get close to each other. We have some general relativity, which tells you how the universe is expanding, which has some thermodynamics, which tells you how the heat is transferred from hot places to cold places. We have some electromagnetism, which tells you how the magnetic fields, both electric and, how the electric and the magnetic field evolves. Then we may have some chemistry, which tells you how molecules form. So all these equations, they can be coupled together. We can write them. And then we again have some initial conditions. So the initial conditions, again, are a bit more complicated than what we had earlier with the simple tennis ball. But it's simply the position, the speed, the temperature, the composition, magnetic field, etc. of the early universe. By chance, observations show that it's somewhat random. So randomness is a bit complicated, but we can reproduce these initial conditions pretty well. And then, of course, these equations are way too complex to be solved. So we feed that to a big computer. So I'm giving here the currently most powerful computer in the world, Fugaku cluster, but there's been a lot of examples previously. And so the Fugaku cluster is as powerful as 2 million MacBook Pro. And then you can use part of it, say, I don't know, maybe 1 or 10% of all the power, and you can solve this set of equations numerically. You evolve the time step of the universe. Here is what it gives. So on the right, you have you can forget about it. It's called the redshift. Maybe it's a discussion for later. But you have T. T is the age of the universe in gigayears. So giga is for 1 billion. So this is around 220 millions of years. So this is the age of the universe. For information, the age of the universe today is about 14 billion years. On the bottom left corner, you have a scale, 300,000 light years. So if you remember very well, the size of our Milky Way is 30,000 light years, okay? So the scale here is 10 times larger than our Milky Way. I will start the video, and you see that as time evolves, the scale reduces because you have the expansion of the universe, and you start forming structures. Again, here, each dot is a galaxy similar to our Milky Way. At some point, the video will stop. It's a simulation that I performed myself. And I had to stop it when the universe was only 1/10 of its current age because I didn't have any more power. There are people who run simulation, and they can go to the age of our universe today, maybe because they have more power, maybe because they study a different problem. But the idea is very similar. You keep evolving your universe. So if you start from initial conditions and a set of equations, using the physics we know, we can naturally reproduce the large structures that I presented in the introduction. And all this is what we have now as a data set, and we can analyze it. For instance, what we can do is to produce fake images. So on the left, this is a similar simulation that I just showed you. And because you know all the stars in the simulation, and you know the age of the star, you know the composition of the star, etc., we can estimate how they would look like in the sky. And we can make a fake image. Here, every dot is not a star, it's a galaxy. So actually, you have thousands of stars which form galaxies. So we can make a fake image of this galaxy, and we can make a fake image of the sky. And on the right, you have a true image of our sky. And the idea is that we can produce this mock image. We can compare this mock or fake image with real images from the sky, and we can test our theories. We can test if the theories are correct. I will show you another example later. So to conclude, we already saw the first 2 bullet points, but to give a summary to this small part, most of the equations that we try to solve today when we are doing research, they do not have an analytical solution. And this is why we have to rely on numerical solutions. One strategy which is usually adopted is to evolve forward the simulation. So you take a small time step, say 1 second, and you say, okay, what will be the state of my system after 1 second? And then you know the state of your system, and then you iterate again, what will be the state of my system after 2 seconds, etc., etc. And once we have used all this simulation, we can produce some fake images, we can analyze these simulations and compare them with reality to check if we have a good understanding of our universe. So this was about the computational research part of the title. Now let me zoom, actually, you will see, onto black holes and understand how we can use all this power, all this computational power for studying black holes, and where do black holes fit, actually, in this universe. So first, what is a black hole? Let's come back to the example of the tennis ball. So this is Earth, the blue planet, and you have 2 tennis balls, 2 very big tennis balls, which are at the surface of the Earth. One tennis ball is with some speed, v0, 10 meters per second. I was using this value earlier. And one other tennis ball has another velocity which is larger than the first one. I'm going to use again the same example. I'm going to throw the ball in the air, and it's going to go up, and go down. And for the second tennis ball, I throw it, but at a much faster speed. And actually what happens is that it escapes the gravitational potential of Earth. If the initial speed is larger than some speed, which we call the escape velocity, then the tennis ball will leave the gravitational attraction of Earth and travel to infinity. So this defines the escape velocity, and you can define it for every body, every celestial bodies. Okay, so for instance, for the Earth, it's about 11 kilometers per second. Now this escape velocity depends solely on the mass of the object, so the mass of Earth, and on the size, the radius of the object. So if you keep the same mass, but you shrink the object, at some point, it will happen that the escape velocity will be larger than the speed of light. And as I told you in the introduction, you cannot go faster than the speed of light. So even a photon will be trapped. And this is what we call a black hole. You will note that this sets the size for the black hole, which we call the Schwarzschild radius. And so typically, when we talk about the black hole, it has a mass, and the size is directly related to its mass. Are black holes big and massive? It's a good question because when we talk about space, as I showed you, usually you have a variety of scales. And so you may want to know where do you fit in this scale. So let's do exercise again, but this time I also added a mass scale. So the Earth, which is typically noted M+, is about 6 × 10⁻²⁴, so that's a 6 and 24 zeros, kilogram. And the radius of the Earth is 6,400 kilometers. If we compare with the Sun is about 1 million times more massive. It's, 300,000 times more massive, okay? So it's 300,000 times the mass of the Earth, about 2 × 10⁻30 kilogram. And the radius of the Sun is 700,000 kilometers. That is 100 times the radius of the Earth. Now, where do black holes fit with respect to these two objects? Well, you have two kinds of black holes. The first, which we call the stellar mass black holes, the mass is typically that of the Sun, maybe 1, 10, 100 times the mass of the Sun. But you see that the radius is only 3 kilometers. And actually, on this image, it's not a picture, it's an image. You can see in the back a star. And here, you can see the black hole. So I don't know if this image is to scale, but at least it shows that even if the black hole is as massive as the star, it's much smaller than the star. So these stellar mass black holes, they are relics of stars. So when a star runs out of fuel, it explodes. And then in the end, you may have a black hole. And they can be found pretty much everywhere in our galaxy. Then there are other kinds of black holes, which we call supermassive black holes. And these are the ones that I study. They are very massive, as you can see, more than 1 million times the mass of the Sun. But their radius is still very small, only 4 times the radius of the Sun. So their formation mechanism is still well not understood. This is part of my research project. And usually we find them in the center of galaxies. I will come back to that in the next slide. So supermassive black holes are way more massive than the Sun. They are 1 million times more massive than the Sun. But they are similar in size. Their radius is typically 4 times the radius of the Sun. So we're talking about an object which is as massive as 1 million Sun put in an object which is typically the size of the Sun. Just a comment. This picture is a true picture. This is what you're seeing so the third one is an image, but the fourth one is a true picture where you see the black hole, so you can't see the photons, and what you see around is matter falling onto the black hole, and then there is friction because the matter is falling onto the black hole, and so this is what you see, what we call the ring of the accretion disk. So the first, one of the most beautiful proof that black holes exist to me is this video that I'm going to show you. This is the center of the Milky Way that we're looking at. So each dot is a star. And I want to insist, these stars are 30,000 light years from us. You have on the top left the year. So this is in 1992. And in the top right, you have a scale to show you 10 light days. And I'm going to start the video. And you're going to see that this region has been observed for a very long time, for like 20 years. We're going to keep zooming. Again, these stars are very far. And what you can see from this star that we call S2 is that it orbits as an ellipse. And if you remember your class from celestial mechanics, the Earth is orbiting the Sun following an ellipse. So this is the exact same process. The Earth is orbiting the Sun following an ellipse, and this star is orbiting something following an ellipse. And actually, you can reverse engineer all the dynamics of the star, and you can know that in the center, there is something which mass is 4 million solar masses. And this is a black hole. This is one of the strongest proof that there is a black hole. And actually, people have been awarded the Nobel Prize last year for these findings. So I told you that in the center of galaxies, there is a supermassive black hole. So let's go back to this image of the galaxy. And again, The radius of this galaxy is 25 to 30,000 light years, and the total mass is 10 to the 11 solar masses. So if the typical mass of a star is 1 solar masses, this means that there is 100 of billions of stars. The Sun is in one of these stars in the outskirts of the Milky Way, so we are very far from the center of the Milky Way. So that is to emphasize how far we were looking in the previous video. And in the center, there is a supermassive black hole. So the size of this black hole is very small compared with the size of the galaxy, and the mass is also very small compared with the mass of the galaxy. Actually, the black hole is much lighter and much smaller than the Milky Way. And the picture that you should have in mind is this, okay? If we were to look at a galaxy from the outside, we wouldn't see at all the black hole because it's so much smaller than the galaxy. But if black holes are so small, both in terms of mass and in terms of size, why do we study them? Are they important to understand galaxies? And one of the reasons we believe they are important is because black holes are a formidable source of energy. So here, it's a video, but it's not a scientific video. Actually, maybe it is, but it's not in the real world. It's a simulation, okay? Here you have a black hole, and here you have a star. And the star is disrupted by the black hole because of the tidal forces. It forms an accretion disk, and then you have a jet which is emitted. And this jet carries a lot of energy and power. Actually, when you have matter which falls onto the black hole, you have a tremendous amount of energy that is radiated, and this is related to the rings that we were seeing previously, even if this black hole is not accreted so much. And probably this tremendous amount of energy and power can couple to the gas, to the stars, maybe push them away to very far distances. And so maybe black holes could actually have an impact on the entire galaxies. And if we want to understand this process, we can use simulation. For instance, I'm showing on the left, again, the similar videos that you've seen earlier, but with red pockets. So when the black hole is accreting, it emits a lot of energy, and so it hits the surrounding gas, okay? And so you can see that black holes seems to have an impact on very large scales. And to show you the wide range, here I'm zooming on one galaxy, so the timestamp is not as good, but you can see that the galaxy is building stars. Every dot in this galaxy is a black hole. So you see that there are a lot of black holes in this galaxy, but there is one which is stuck in the center, okay? Maybe there's gonna be a merger. Oh, we passed it already. But what I want to emphasize is the different scale. You see that the scale on the bottom left of this image is 300,000 light years, and on the bottom right, it's 3,000 light years. So that is 100 times, it's a zoom of 100 times, if you want. So how can we study black holes? How can we use these simulations to study black holes? I've shown you a simulation with black holes, but how can we use this simulation to actually probe the effect of black holes? Well, if you want to study the effect of something, the usual strategy in science is to do one setup with this something and one setup without this something. So let me give you an example. If you want to study what is this nerve used to, you're going to take one human and you're going to remove the nerve. You're going to cut it, okay? And then you're going to take another human and you're not going to cut this nerve. And you're going to realize that the human who still has the nerve can still move his arm, okay? And then you can show that this was the reason of the nerve. You can do a similar example with the vaccine, for instance. You take a population with vaccine, you take a population without vaccine, and you look how many people die, okay? If the population with vaccine, without vaccine doesn't die as much, then you can show that the vaccine has a positive impact on your health. What you want to do is the exact same thing, but with black hole. So what you would want is a universe with black hole and a universe without black hole. The issue is that we have only one universe. So we have to go into the simulation, and we do one simulation with black hole, which we call Horizon AGN. AGN is for Galactic Galactic Nuclei, Basic Active Galactic Nuclei. These are basically black holes. And one simulation without black holes. The exact same setup, the exact same initial condition, the exact same physics. The only difference is that in the left world, in the left universe, you have black holes, and on the right universe, you don't have black holes. And then you can look at your universe, which has black holes, we know it, and you can look which of these universe is better. Which of this universe better reproduces our real universe. So it's going to be the most complex plot of this talk, so I'm going to take some time on it. I think I forgot to say what we're going to do actually. So what we're going to do, here I told you that every dot is a galaxy, and we can measure the mass of this galaxy. And so we're going to count in this volume, okay, how many galaxies of a given mass we have. And we're going to do the exercise on the left universe, the exercise on the right universe, and we're going to take our real universe with our real telescope with a similar volume, okay? We're going to shrink it such that it has a similar volume, and we're going to look at how many galaxies of a given mass there is in this volume. So let's come back to this plot. So on the y-axis, you have the number of galaxies with a given mass in a given volume. The units are not very important. What you need to know is that when you go up, you have more galaxies, and when you go down, you have less galaxies. The x-axis of this plot is the mass of the galaxy in units of solar masses. Again, the units are not very important. What you need to know is if you go to the right of this plot, you have more massive galaxies. And if you go to the left part of this plot, you have less massive galaxies. And then we have a lot of curves. It's a very busy plot. But let me go slowly on it. The pink line is a numerical universe without black hole. So you simulate your universe and you assume that there are no black holes. The gray line is the exact same universe in which you have removed black holes. So this is a universe with black holes. And the colored lights, yellow, green, and blue, are observations. So people went into images produced by telescope, and they told and they measured how many galaxies you have in a given volume as a function of mass. So this is the real universe, which we know has black hole. If you look at the left part of the plot, they all look very similar. So it seems that black holes are not very important for these galaxies, and that maybe black holes are not very important for understanding galaxies in general. But if you go to the right part of the plot, you see that the numerical universe without black hole, that is the pink line, is not able to reproduce observations of our real universe. However, the exact same universe in which we have included black holes, the gray line, is able to reduce the number of galaxies, to quench galaxies, this is the way that we use, in the high mass end. So this is an indication that black holes are essential to understand galaxy evolution, especially in the high mass end. So black holes are regions, so again, we've seen the two first lines. So black holes are regions of the universe where even photons which travel at the speed of light cannot escape. They have a mass ranging from few to million billions solar masses, okay? But they remain very small compared with the typical scales of the universe that we have seen. Usually, we find a supermassive black hole in the center of galaxies, and when they accrete material, they radiate a tremendous amount of energy. And as I have shown in the last picture, this can affect the entire galaxy, and we have shown that with numerical simulation. By we, I mean the scientific community. Now let's finish the last part of this talk and talk about artificial intelligence in astronomy. So maybe just one slide about artificial intelligence. The definition from Wikipedia is to construct a system that maximizes chances of achieving some goal. So what kind of goal can we have? We can have classification. Okay, so for instance, you're showing an artificial intelligence an image, and you're asking the artificial intelligence, which animal is it? Is it a dog? Is it a cat? We call that a classification problem. And then you can have another kind of problem. For instance, you have done an experiment where you have measured some quantity y as a function of x, and you're wondering what could be the value for this new x. You haven't made the measurement. You haven't made the experiment, and you don't have any more money to make the experiment. What will be the value here? Naturally, you want to put it here, but there are ways to do that, to explain that to a computer, that the value should be around this value. And this is the other goal of artificial intelligence, which is to predict. In astronomy, we use artificial intelligence to understand galaxy mergers. So I'm showing here a simulation where you have two galaxies, two black holes. You have time here and the scale again. And you see that the two galaxies were into a merger. And then they are dancing one into another. At some point, they form a big galaxy, and the two black holes, they meet in the center, and they form a binary black hole. So this is a simulation, and it indicates that we form a more massive galaxy. When you look at the amount of stars in this simulation, you can find that there is a lot of stars that got formed during the merger. So this simulation indicates that you enhance the formation of stars when you have a merger. And this simulation also indicates that when you have a merger, you can have the formation of a binary black hole. All this, we can understand it with numerical simulation because we can track the dynamics as a function of time. But can we do that with observation? And the answer is a bit difficult. If you see this gorgeous image of two galaxies, then you may say, okay, let's come back later and see if the two galaxies are moved. But the issue is that this process is going to take 1 billion of years. So if you take, even when you start your career, you take this picture, at the end of your career, the picture is going to be the exact same. So you have a temporal issue, and this is usually an issue in astronomy. But it's not the only issue. You have a spatial issue, because you cannot move around galaxies. And to show you what I mean by that, if you look at these dots, it seems that the blue dot and the green dot are very close, and they are both far from the orange dot. But if we were able to turn around, it would appear that the green dot is actually much farther than the two other dots, and that the orange dot and the blue dots are very close. This is what we call a projection effect, and this is what I mean by spatial issue in this process of determining if two galaxies are merging. So here we can see tails here, for instance, and it seems that these two galaxies are indeed merging, but in some cases it can be very hard. So for instance here, when we look farther away, every dot is a galaxy. Is this galaxy merging with this one? Is this galaxy merging with this one? You can see that it's very difficult to conclude from this image. So the strategy is to couple numerical simulation with artificial intelligence. So I already showed you this video where you have the formation of structures, and I've already told you that this simulation is very realistic. We can reproduce the number of galaxies very well. But then I've also showed you that you can zoom on every galaxy, and you can say, oh, okay, here there is a few galaxies. You make an image, and there are a few galaxies here, a few galaxies there. But because it's a simulation, you can follow these galaxies as a function of time. You know the position, speed, velocity, etc., mass of every galaxy as a function of time. And more importantly, you can know if they merge or if they don't merge. And with this, you build what we call a training set. So the training set is very important in artificial intelligence because then you can show your algorithm and you can tell, okay, this galaxy is merging because actually this galaxy This galaxy is not merging, sorry, because actually this one is not merging. This galaxy is merging, and the algorithm sees all these examples, and it learns, even if for us it's very difficult to see the difference, the algorithm starts to understand what makes a pair a merger or a non-merger. And actually, we have trained an AI algorithm using this process, and hopefully, this algorithm will be used later on real data to actually find if two galaxies are merging or not. And again, I want to emphasize, even if our eyes, they cannot make the difference between this image on the left and this image on the right, we know that the left one is non-merging because we can measure that in the simulation. We know that the right one is merging because we can measure it in the simulation. And the algorithm will be able to understand what makes an image a merging image and what makes an image a non-merging image. So this brings me to the conclusion of this last section. I've shown that AI starts to be widely used in astronomy. In particular, you make mock images using numerical simulations, and then you train your algorithm, and hopefully you apply it then to observations. And I've shown you one example where we use artificial intelligence to actually understand if two galaxies are merging or not. Thank you very much for your attention, for listening